The picnic near the lakeside in Chicago is the start of a lazy afternoon, early 1 October. We begin with a scene 1 meter wide, which we view from just 1 meter away. Now, every 10 seconds, we will look from 10 times farther away, and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds, the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Powerboats lie at their docks. The colorful bleachers are Soldiers Field. This square is 1 kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake. 10 to the 5th meters. The distance an orbiting satellite covers in 10 seconds. Long parades of clouds, the day's weather in the Middle West. 10 to the 6th, a 1 with 6 zeros, 1,000,000 meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey. The Earth diminishes into the distance, but those background stars are so much farther away that they do not yet appear to move. A line extends at the true speed of light. In 1 second, it half crosses the tilted orbit of the moon. Now we mark a small part of the path in which the Earth moves about the sun. Now the orbital paths of the neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the sun, followed by the massive outer planets, swinging wide in their big orbits. That odd orbit belongs to Pluto. A fringe of a myriad comets too faint to see completes the solar system. Ten to the 14th. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one among the stars. Looking back from here, we note 4 southern constellations, still much as they appear from the far side of the Earth. This square is 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last, we pass the bright star Arcturus and some stars of the Dipper. Normal but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way galaxy. Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The 2 little satellite galaxies of our own are the Clouds of Magellan, 10 to the 22nd power, 1,000,000 light years. Groups of galaxies bring a new level of structure to the scene. Glowing points are no longer single stars, but whole galaxies of stars seen as one. We pass the big Virgo cluster of galaxies among many others, 100 million light years out. As we approach the limit of our vision, we pause to start back home. This lonely scene, the galaxies like dust, is what most of space looks like. This emptiness is normal. The richness of our own neighborhood is the exception. The trip back to the picnic on the lakefront will be a sped-up version, reducing the distance to the Earth's surface by 1 power of 10 every 2 seconds. In each 2 seconds, we will appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative inactivity, a rhythm that will continue all the way into our next goal, a proton in the nucleus of a carbon atom beneath the skin on the hand of the sleeping man at the picnic. 10 to the 9th meters, 10 to the 8th, 7, 6, 5, 4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter, 10 to the 0 power. Now we reduce the distance to our final destination by 90% every 10 seconds, each step much smaller than the one before. At 10 to the minus 2, 1/100th of a meter, 1 centimeter, we approach the surface of the hand. In a few seconds, we'll be entering the skin, crossing layer after layer from the outermost dead cells into a tiny blood vessel within. Skin layers vanish in turn. An outer layer of cells, felty collagen. The capillary, containing red blood cells and a roughly lymphocyte. We enter the white cell. Among its vital organelles, the porous wall of the cell nucleus appears. The nucleus within holds the heredity of the man in the coiled coils of DNA. As we close in, we come to the double helix itself, a molecule like a long twisted ladder whose rungs of paired bases spell out twice, in an alphabet of 4 letters, the words of the powerful genetic message. At the atomic scale, the interplay of form and motion becomes more visible. We focus on one commonplace group of 3 hydrogen atoms bonded by electrical forces to a carbon atom. 4 electrons make up the outer shell of the carbon itself. They appear in quantum motion as a swarm of shimmering points. At 10 to the minus 10 meters, 1 angstrom, we find ourselves right among those outer electrons. Now we come upon the 2 inner electrons held in a tighter swarm. As we draw toward the atom's attracting center, we enter upon a vast inner space. At last, the carbon nucleus, so massive and so small. This carbon nucleus is made up of 6 protons and 6 neutrons. We are in the domain of universal modules. There are protons and neutrons in every nucleus, electrons in every atom, atoms bonded into every molecule out to the farthest galaxy. As a single proton fills our scene, we reach the edge of present understanding. Are these some quarks at intense interaction? Our journey has taken us through 40 powers of 10. If now the field is 1 unit, then when we saw many clusters of galaxies together, it was 10 to the 40th, or 1 and 40 zeros.
And what happens if we try to get there? You might be thinking, wait, how is there an edge to the universe if it's infinite? This gets talked about a lot, and people usually say one of the following. The universe defines all of space and time that exists. Well, that's one definition of universe, but is it even part of our universe if we can never interact with it? And what if our universe is very, very different beyond the edge? The universe is infinite because general relativity tells us that the universe is demonstrably flat, and therefore the galaxies go on forever. But how flat? Are you sure you measured the universe's curvature with infinite precision? And my favorite, we can never know and never test it, so it's not even a scientific question. Oh yeah? I'll science any question I please. This is space-time. Okay, sorry. Before we get carried away, let's talk about the edge or edges of the universe and what it might take to get there. In a previous episode, we talked about the size of what we call the observable universe. We even gave you a number, 93 billion light years in diameter, 46 billion in radius. Go ahead and watch it again. It'll be useful. While you're at it, we're also going to be talking about the CMB, so it wouldn't kill you to watch that episode also. Okay, let's start with that 46 billion light year number. We defined that as the current radius of the known universe. It's the distance to that blob of the CMB, the most distant thing we can see in that direction. Now, it's not 46 billion light years to that actual blob. It is currently 46 billion light years to whatever galaxy or galaxy clusters that blob evolved into. racing away from us with the expanding universe as it did. We call this the particle horizon of the universe. It's the current instantaneous distance to the most distant part of the universe that could possibly have a causal connection to us. Anything inside the particle horizon is referred to as the known universe. Now, when I say the current instantaneous distance, I mean it's the distance that you would have to travel only if the universe froze in its expansion and you were traveling through static space. In cosmology, this sort of instantaneous distance is basically what we call the proper distance between 2 points. But nothing actually ever travels the proper distance. That's not how space-time works. The shortest path in space-time is defined by the geodesic, the path of light between 2 points. Even light takes time to make any journey, so we have to factor in the time interval, especially when space is changing. To travel to the particle horizon, we need to move through expanding space. And the closer we get to our destination, the more space will have expanded over the remaining distance. How far would you have to travel? Bad news, you'd have to travel infinitely far, even if you were in a spaceship that could travel at the speed of light. Just as black holes have event horizons, so too do universes. The event horizon of a black hole is that point beyond which we can never receive information because light from that point is redshifted into oblivion. It's a boundary to the observable universe. There's a region of this universe from which we can never receive any new signal. That is, any signal that's emitted today. This is because the distance that signal has to travel to get to us will be expanding faster than the speed of light before the signal reaches us. Same thing applies to our light speed spaceship. We can never get to anything beyond the cosmic event horizon because that space will be moving away from us faster than light before we reach it. Now here's where it gets weird. The event horizon of the universe is actually closer to us than the particle horizon. Given our best measurements of cosmological parameters, we think that the cosmic event horizon is around 16 billion light years away. This means that there are galaxies that we can see now that we could never reach or even communicate with. We're sort of seeing ghost images from outside the part of the universe that we could ever interact with. As our universe expands, more and more of it will cross the event horizon, and eventually almost all of it will be lost to it forever. Kind of sad, really. Of course, all bets are off if we can break the cosmic speed limit, so let's do just that. There's no doubt that Einstein was right in setting that limit for objects moving through space, but two regions of space can have superluminal relative speeds. That's actually the motivation behind the warp drive, which we might get to in a later episode if you're up for the challenge. But for now, let's just assume we have a nice Alcubierre class warp ship and we burn the mass energy of entire stars to chase the particle horizon. What do we find? Almost certainly, just more universe. Bummer. Remember, the particle horizon is just defined by the limit of our current view. Move to my left, and my observable universe moves with me. Wait a minute, and my particle horizon expands. Travel to the particle horizon instantaneously, and you'll see the Milky Way as a cute baby CMB blob on your new particle horizon, and presumably, a pretty similar distribution of galaxies and clusters all around you. But what if we keep going? What's far beyond that edge? Well, that all depends on the geometry of the universe. On the largest scales, the geometry of space-time is very flat. It's lumpy on small scales due to stars and galaxies, but smooth on large, sort of like ripples on the ocean. Measurement of the distribution of galaxies and the CMB confirm this flatness with very high, but not infinite, precision. If space-time really is perfectly flat, then with the most simplistic application of Einstein's equations, we get that the universe is infinite. Now, people claim this a lot. So, if it's true, what happens if you cross the particle horizon? The universe just goes on and 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 on, and infinity is its own amazing beast, and there are many types of infinity, including some that involve infinitely repeating versions of this bit of the universe. But is our universe really perfectly flat? Think about it this way. The surface of the Earth looks pretty flat to us because we really can't see the curvature locally. But get some perspective by taking a ride on the International Space Station, and it's clearly curved. What if the curvature of the universe is so small that we're just not seeing far enough or measuring precisely enough to detect it? It's very possible that the universe has curvature just inside the uncertainty range of the best measurements to date. If that curvature is positive, then it may be that the universe is really the surface of a hypersphere, the 3D surface of a 4D sphere. In that case, our warp ship would eventually travel all the way around this curved hypersphere and get back to where it started. Okay, so how far would it have to travel? Based on a recent estimate of the minimum radius of curvature of the universe, you'd need to travel an absolute minimum of 18 times the distance to the particle horizon to get back to where you started, assuming expansion froze for the whole journey. We also have to keep in mind that these geometries assume that we can just extrapolate Einstein's equations in the most simplistic way. In addition, although general relativity is pretty cool, it's not a theory of everything. Non-crazy ideas for the origin of cosmic inflation suggest that our universe may just be a slowly expanding bubble in an exponentially, infinitely inflating multiverse. Now, bubble universes may be finite in size, regardless of internal geometry, and so they may have a true edge. But what's on the other side? Are the laws of physics or even the number of dimensions the same?